Well, it's, sorry, 2:23 on Wednesday, the 31st of October, which happens to be Halloween, and maybe I'm being played a trick or treat on here, but I'm in the room by myself. And but that's how I usually start most of these Cal 3 classes. Hopefully someone will be coming in later. But sorry. Trying to finish eating lunch, and I didn't finish, so I'm sort of clogged up right here. Sorry. What we were doing at the end last time in 13.5, we're in Chapter 13, Functions of Several Variables, and we just started talking about implicit partial differentiation. And Theorem 13.8 is where we're beginning today, and that's this one. Now, hold on just a second. Accidentally or forgot to turn off the computer projector. I thought I had, but evidently it didn't take on my way out, so it was running, and I don't need it running with no one in the room. So anyway, here is the Theorem 13.8, which is a chain rule for implicit differentiation, partial differentiation, okay? If the equation f of xy is equal to 0, now there's the big key. You've got to write the equation f of xy, this is capital F of xy, is equal to 0, defines y implicitly as a differentiable function of x. There's the second thing. First, the function has to equal 0. Secondly, y can be implicitly defined by that as a differentiable function of x. Then, your dy dx, what that is minus the f sub x, the partial of the capital F with respect to x of xy, divided by the partial of f with respect to y of xy. Now that's assuming, of course, that f sub y at xy is not equal to 0 for any values x and y in that domain. Sorry. If the equation f of xyz in 3 dimension is also equal to 0, defines z implicitly as a differentiable function of x and y, then now it's a partial of z with respect to x. Before, it was the derivative of y with respect to x, and the reason for that, of course, is that y is just a function of x here, but here z can be a function of x or y, so the partial of z with respect to x is the minus the partial of f with respect to x at xyz divided by partial of f with respect to z at xyz. Same thing for a partial of z with respect to y is minus partial of f with respect to y of xyz divided by partial with respect to z of xyz. And in both those cases, f of xyz cannot equal 0 for any values xyz in the domain. Now, I don't know any super easy way to remember this, but here's what I use. Notice in the top one here, dy dx, with all these conditions met, dy dx has the partial with respect to y in the denominator, partial with respect to x in the numerator. So that's one way to think of it. Or the other way, partial with respect to y, the derivative of y with respect to x, the numerator is a partial of f with respect to x. So the x's are in the same place there, but then the y's are flipped over, which, that's partial with respect to y. And if you think of dividing by that, that would be would put the dy on top, or partial y on top. Same thing here, your z's on top here, z's in the bottom there, x is on top, bottom here, top there, same with z and y over here. Or, think of it this way, partial of z with respect to x, this is partial of f with respect to x, and then this is 1 over partial of z with respect to x, which would sort of be like the partial of x with respect, f with respect to, or z with respect to f, which would flip it over and put it where it belongs. I don't know. I like to remember the The subscripts are opposite from what the variables are otherwise. Okay? Let's do example 6. All right. Find dy dx for y cubed plus y squared minus 5y plus minus x squared plus 4 is equal to 0. That certainly fits the bill that capital F of x and y is equal to 0, because that is equal to 0. So this thing right here is your capital F sub x and y. Only variables that got in. So then what's your dy dx? Okay. Minus the partial with respect to x divided by partial with respect to y. Just reverse those subscripts. Okay. So let's see. What is your partial with respect to x? Partial with respect to x is minus 2x. That's all she wrote. Sorry. For partial with respect to x. Divided by, and this is a minus in front, remember, okay, the partial with respect to y. Well, that's a 3y squared plus 2y. Okay? That's it. Okay? Now, if you want to clean it up a little bit, the minus and minus go to plus, so 2x over 3y squared plus 2y. And that's all I can think of to simplify it. Didn't say do it at any particular point. I'm sorry. I missed a minus 5. Sorry. Minus 5. There's another y term. Okay. Now I think I've got it. I'm so sorry about my throat. Okay. So 2x over 3y squared plus 2y minus 5. All right. That's how we did it, with one silly error. Let's see how they do it. And again, I said that is your f of xy because it's equal to 0. Then do the partial of f with respect to x is minus 2x. The partial of f with respect to y is 3y squared plus 2y minus 5, the one I've neglected. Then using the theorem, just plugging and chugging, dy dx is equal to minus the partial of f with respect to x over the partial with respect to y, which would be minus a minus 2x over 3y squared plus 2y minus 5, which makes it just 2x over 3y squared plus 2y minus 5. All right. So that was it for example 6. They do have in the book example 7 that they don't have on the slide set, so let's do example 7. This one says find partial of z with respect to x and the partial of z with respect to y. Okay? My leg hurts. For 3x squared z minus x squared y squared plus 2z cubed plus 3yz minus 5 equals 0. Okay, with that equaling 0, we have a perfect candidate for our capital F. Okay. Now, sorry. Here, let me just throw out a suppose here. I probably should have done it on the last one, but what if this would have been everything here is equal to 5? You know, that minus 5 is on the other side. That wouldn't look like it would fit the bill, but all you have to do is move the 5 over and make it equal to 0. It could have even been is equal to x squared y squared plus 5 if this had been on the other side. Well, okay, just move them to one side, get it equal to 0, then use that as your capital F. Okay, so this thing here is our capital F. Now it's a function of x, y, and z. So it asks for partial of z with respect to x, and that gives us minus the partial of f with respect to x over partial of f with respect to z. Again, just sort of reversing those two. That to me is the easiest way to think of it. Okay? So we need to figure out what partial of f with respect to x is. When the first term is going to be a 6xz. The next term a minus 2xy squared. Nothing from the third term, nothing from the fourth term, nothing from the fifth term. So there we have our partial with respect to x. So I'm going to write it down as a minus 6xz minus 2xy squared divided by. Now let's do partial of f with respect to z. Okay. That's a 3x squared in the first term, nothing from the second term, a plus 6z squared in your third term, a plus 3y from your fourth term, and nothing from the fifth term, so that gives us 3x squared plus 6z squared plus 3y. Now the only thing I would do to straighten this up, and it's not necessary, but to me it makes it a little better, reverses these two, which negate them, and that takes out the minus sign, and that gives you a 2xy squared minus 6xz over 3x squared plus 6z squared plus 3y. All right, that's what we got. Let's see what they got. They did the same thing. 2x squared y minus 3z. Whoa, 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 whoa. Did I copy something wrong? 3x squared z minus x squared y squared plus 2z cubed plus, it looks like I copied everything right. Did I do my partials right? Partial with respect to x is 6xz minus 2xy squared, and that's it. Oh, sorry. I was looking at the wrong answer. Okay. Yeah. The partial of z with respect to x is 2xy squared minus 6xz over 3x squared plus 6z squared plus 3y. Exactly. I was looking at the bottom, which is partial of z with respect to y, which will also be a negative, but this time it's f sub y on top, so that we need to calculate. Your f sub y is equal to nothing from the first term, to a minus 2x squared y from your second term, plus 3z from your fourth term, and that's all, folks. So you have a minus in front, and then you would have minus 2x squared y plus 3z over, same denominator, f sub z stays the same, 3x squared plus 6z squared plus 3y, which is equal to 2x squared y minus 3z over 3x squared plus 6z squared plus 3y. Now, I didn't notice, should have, you could factor out a 3 from the denominator. It doesn't really help you any, but you could do that. So your partial of z with respect to y is 2x squared y minus 3z over 3x squared plus 6z squared plus 3y. Now, one thing they didn't mention here, and it's certainly true, it's not necessary, I think, at all for it to only be with regard to the second function, last function, I'll say, z in this case. You could have done a partial of x with respect to y. You could have done a partial of y with respect to x, partial of x with respect to z, partial of y with respect to z. You could have done any of those partials using these same rules. Of course, you'll change your partials with respect to x, f with appropriately, but you could have done them. There's nothing really special that z has to be the one that you solve for, because pretty obvious they're all mixed up just as much as any, so there's one doesn't have any right over the others to be the one you always take the partial of that function with respect to the other two. Okay. That's it for 13.5. Homework exercises. I've assigned most of these before. I'll do them again. Do either 3 or 5. They're both at calcchat.com. 3's at CalcView. Do any of the odds 7 through 11. They're all at CalcChat. 9's at CalcView. Do 13. It's at CalcChat. Do either 15 or 17 or both. They're both at CalcChat. 15's at CalcView. Do either 19 or 21. They're both at CalcChat. 19's at CalcView. Do either 23 or 25 or both, and they're both at CalcChat. 23's at CalcView. Do any of the odds 27 to 33. They're all at CalcChat. 31's at CalcView. And then the things we did, well, that I guess started a couple earlier, started were the new stuff, but now do any of the odds 35, either 35 or 37. They're both at CalcChat. If I didn't know, yeah, I think I said the other. Do 39 or 41. They're both at CalcChat. Do 43. It's at CalcChat. 45 and or 47 should be at CalcChat. That's using the chain rule. 49, 51, 53, or 55 all could be done if you choose, and they should all be at CalcChat. Now, just looking at some of those toward the end, ideal gas law is featured in number 50 that you don't have to do, but if that's something you want to write a paper topic on, you might find at least that title here. Moment of inertia, again, something you're not needing to do, but it's an example of such a thing. That's 51. 53 features the Cauchy-Riemann equations. And if you haven't already run into Cauchy, I think you probably have. Certainly, if you've run into the name Riemann, you can certainly look at those. That's 53 and 54. And then they're talking about a homogeneous function in 55. And that's something you're going to run into when you take differential equations, if you do take it. And so just to get you a little heads up there, that I can't really imagine writing a paper on that so much, but maybe you could find enough to do so. All right, that finishes 13.5. Let's move on to 13.6. And as I mentioned in my first class this morning, somebody said something, or for some reason I mentioned it. I said, yeah, and today is the last day to get your paper in and get 2 bonus points, because tomorrow it'll only be down to 1 bonus point. And that prompted someone to run down to the library or somewhere else, knock out a paper, and bring it by to me in my second class. So same with you. If you can get me the paper today, which means 31st of October, you get the 2 bonus points. If you get it to me tomorrow or any time in the month of November, it's down to 1 bonus point. All right. So let's move on to 13.6 on page 919. Let me get the PowerPoint set up for this. There we go. Wrong. I don't know why that happened. Here we go. All right, another really long chapter, folks. Now, we're probably not going to do all of these, but we do need to do 13.6 for sure. One of the, I want to say prime, I'm not sure that's the best word, illustrations of partial derivatives when you're dealing with, of course, functions of several variables, meaning several independent variables, and doing partials. You come up with what they call directional derivatives and gradients. Okay. and my guess, the lower left picture is the one we're going to be dealing with here. I don't know that for sure, but my guess would be that one. Okay, 13.6. Directional derivatives and gradients. What do we mean by this? Well, here are our objectives for 13.6. Find and use directional derivatives of a function of two variables. So part of that is also defining and finding and using directional derivatives of a function of two variables. Okay? Find the gradient of a function of two variables, which is one step beyond that. Use the gradient of a function of two variables in applications, and then finally find directional derivatives and gradients of functions of three variables. So we'll start with the twos to begin with, and then we'll move on to threes. Three variables. All right, first, directional derivative. What in the world is this? The figure that's in your book is here, figure 1342. You're standing on a hillside represented by z is equal to f of xy, where x and y are, think of them as flat, planar ground that's underneath the hill, somewhere way under there. X is in one direction, y is in the other. Say x in the east, y is in the north. Something, just follow the right-hand rule. Okay? X, y, and then z would be up. You're standing on that hillside represented by alpha. Z is equal to f of xy in that figure. You want to determine the hill's incline toward the z-axis. You already know how to determine the slopes in two different directions. The slope in the y direction is given by partial derivative f sub y of xy, and the slope in the x direction is given by the partial derivative f sub x of xy. In this section, you will see that these two partial derivatives can be used to find the slope in any direction. Okay? All right. So, basically, to look at this picture, again, the xy plane is somewhere underneath the hill, okay? That's the basis for it all. Z is straight up, so that makes x, y, z, orthogonal system, right-handed rule, all that kind of stuff. The surface of the hill now is basically a function. Z is some function of those x's and y's. And they projected the xy grid pattern in the first octant, you might call it, upward through the hillside, indicating that's the domain over which this hill rests, especially in the first octant. Okay. Now, to determine the slope at a point on a surface, you will define a new type of derivative called a directional derivative. This isn't just with respect to one axis or another. It's a directional derivative, okay? All right. Let's begin by letting z be some function of alpha of xy. And that makes perfect sense here, and it makes perfect sense here in figure 1343. I'm just going to okay. All right, so z of f of xy is a surface. The hillside, this smooth surface over here, whatever. P at x0, y0 is some point on that surface, but it's in the domain of f. So the x's and y's have to be defined for that value f. Okay? Now, this figure, you can't tell where P is. It looks like it could be on the x-axis. It's not. It's on the surface above. The direction of the directional derivative is given by a unit vector u which is cosine theta I plus sine theta j, where theta is the angle the axis makes with the positive x-axis. Okay? All right. I hate to do this because I was going pretty well, but my head is getting voice and head is getting more and more stopped up. So let me pause for just a minute here and go get something to drink. I realize now, as I've done before, I tried to cram down as much as lunch as I could and did not drink enough, and now that's getting to me. So I will be back in just a few minutes. All right, sorry I'm back. I'm not sorry I'm back, but sorry I had to take a break. But I'm back now. I'm not sure my throat's any better, but I did try to drink something to loosen it up some, but still not great. Okay, so to find the slope, we were talking about it before, the direction of the directional derivative is given by a unit vector. I guess we did this. I thought I had. Okay. Maybe not. Okay, let's start back over here. To determine the slope at a point on a surface, you define a new type of derivative called a directional derivative. Okay. Not just with respect to one axis or the other, those are directional derivatives in a sense, but this is a derivative that's not dependent on an axis. So we start by letting the slope be z of some function of x and y. Remember, xy is, we talked about this, is that horizontal surface, you might say. Underneath, z is the vertical mapping of the function onto space above that slope, that surface, okay? P of x0, y0 is a point on the domain of f, and this, I think, is what I was trying to mention before. In a graph such as this, it's hard to see where the P is. That P is supposed to be on the surface of that curved shape there. It's not somewhere down near the x-axis. Okay, it looks like it is. That's not what, well, at least I don't think that's what it's talking about. Okay? But the line that P is on, well, we'll get to that in a second. So there's P at some value x0, y0. Up there on the surface, okay? Now, so P of x0, y0 be a point, no, I'm sorry. It is down on the xy plane. They just drew it right near the x-axis. P is a point in the domain, which is the xy plane. So it's down there on that sort of the gray shape down the rectangular looking shape down there on the xy plane. So it's not a point on the surface, it's the point on the plane, x0, y0. Okay? It's a point, not a function. I was thinking it was a function. It's not. Just the point, x0, y0. The direction for the directional derivative is given by the unit vector u is equal to cosine theta I plus sine theta j, which if you think back, I think many of you have had physics, cosine refers to the adjacent side, which is the x side typically, and y, the y side or the is the opposite, which is the sine, relates to the opposite to it. So sine theta j. Where theta is the angle between angle the vector makes with the positive x-axis. Okay? Now, it's a unit vector, okay? They show coming from the origin, but the angle theta is the same as the angle theta there, okay? So this line that P is on is parallel to that unit vector because their angles are the same, okay? What is not completely clear is how they determine what direction L was going to be. They show the P not quite on the x-axis and just drawn from some point on the x-axis. It doesn't seem, and definitely isn't perpendicular to the x-axis, not the way it's drawn here, because they show an angle theta rather than a 90-degree angle. So there's nothing yet that tells us what direction that U should be in. It's along that L, which contains P on it, but what is special about that line? Hold on, we don't know that yet. Where theta is the angle the vector makes with the positive x-axis. Okay? Okay. So I think, in a sense, we sort of got things a little backwards here. There is a point PXY, x0, y0, okay? That's somewhere there on the domain, the xy plane down there, okay? You've been given a unit vector, cosine theta I plus sine theta j. That depends on the theta, and that's why I think that should have been the theta they wrote in first, because that's what defines it. And of course, these are the dimensions, or the components of that vector in the xy direction. It's cosine theta for I and sine theta for j. Of course, because the hypotenuse is 1, okay, because it's a unit vector. All right. Then you draw a line parallel to that vector, the unit vector, through P from the, say, x-axis, and that gives you the line L. So it's not that you came up with the line L first with that angle theta. There was no reason for it. You came up with the unit vector with that angle theta. Okay. So to find the desired slope, reduce the problem to 2 dimensions by intersecting the surface with a vertical plane passing through the point P parallel to that unit vector. So yeah, the unit vector, the direction, and that's what this unit vector is doing, basically giving you a direction. Because you see it's a unit, so unit in length, so you know the length is 1. There's nothing special about the length, it's 1, okay? What's special about the vector is its direction, okay? So draw a plane, like they said, a vertical plane passing through the point P parallel to that vector U that you're interested in anything in that direction, okay? That vertical plane intersects the surface, that Z surface up there, to form the curve C. Okay? Now, the slope of the surface at x0, y0, those are the components for P, and then f of x0, y0, the point up on the surface corresponding to that P down in the domain, that slope of the surface there is defined as the slope of the curve at that point. Okay, so for this one up here, it would be, let me get my pen to black here, that would be sort of in this direction. So there would be the slope, slightly negative. The change of z per change of xy would be in the negative direction. If both x's and y's are changing in the positive direction. So that's the slope at the surface at that point above P. Okay. Now, they put a few more parameters on here that we're not going to deal with quite yet. They've got another point out here, Q, and they have a parameter T. Now, they haven't indicated what that T is. Sometimes T stands for time, and that would kind of make sense if the point was moving on the line L that they had listed before in the direction of Q, then that would be the time it took to get from P to Q. if that's what it stands for. It doesn't have to be time, okay? Now, but that point Q is actually going to be a variable point, xy, f of xy, where the point P is a fixed point at x0, y0, and f of x0, y0, which is the z value at that point. The Q point is going to be your variable point, and for right now, it's going out that plane, along the intersection of that plane with the surface z. Okay. All right. Informally, you can write the slope of the curve C as a limit that looks much like those used in single variable calculus. The vertical plane used to form C, oh, the curve C, that's right. I was thinking it meant a point C, and I said planes don't. Okay. Curve C intersects the xy plane in a line L represented by the parametric equations, and this is where the t comes into play. X is equal to x0 plus t cosine theta, and y is equal to y0 plus t sine theta. Okay? So that was the thing that was a little suspicious at first. They drew the line in here on that slide, I guess it's slide 6, way before they told you why they were doing it. In fact, there was no need for it yet, and that's what made it sort of confusing. That's why the theta looked like it was drawn from that line. No, it was drawn from the unit vector, so that's why I drew it there. But it's parallel. Okay, so anyway, that's your setup. We don't use it until we get here. And there's a t they show in this one, but don't tell you what that's about. Over here, they all make sense now. Okay, that vertical plane intersects the xy plane in that line L, represented by the parametric equation. The x value for that, any other point on that line L, will be x0 plus t cosine theta, which is your initial x value at the point P, plus, and then any t times cosine theta tells you how much it's moved along the adjacent side, the x side, okay? And the y is equal to y0 plus t sine theta, okay? So that for any value of t, the point Q of xy the point Q of xy lies on that line L, okay? All right. For each of the points P and Q, there is a corresponding point on the surface. Sorry, I'm losing my voice again. On the surface, x0, y0, f of x0, y0, that's the point that's directly above P, and xy, f of xy, which is the point directly above Q. Remember, I called Q our variable point, where it's not a specific value x0 and y0, but a generic one, xy, and then f of xy. Okay? So again, the verbiage here matches what we were seeing back on that slide. All right. Moreover, because the distance between P and Q, that's back here, that distance down there that's related to that variable t, the distance between P and Q is the square root of x minus x0 squared plus y minus y0 squared, okay? Which is x being t cosine theta, here, x minus x0 is t cosine theta, y minus y0 is t sine theta. So that's where you get those. Well, guess what? Square root of t squared cosine squared theta plus t squared sine squared theta, factor out a t squared, and you get t squared times cosine squared theta plus sine squared and you can write the slope, sorry, voice is going again. You can write the slope of the secant line through these 2 points, x0, y0, f of x0, y0, xy, f of xy, as okay, let's go back and look at this for just a moment. Now they're talking about let's go back here. This distance between P and Q, physically between P and Q, they're saying is related, certainly related to that T. They're actually saying it is the absolute value of that T, and that's where they go about proving it. Okay? Now, it says you can write the slope of the secant line through, now this is x0, y0, f of x0, y0. That's this point up here and that point. So the secant line between those two, that would be the straight line that connects those 2 points on that curve. That line it would be, the slope is the change of your z value, which is f of xy minus f of x0, y0, change of z, over your change of xy in the domain. Well, that change of xy in the domain is that value t that we defined before, the parameter that does that. So, expanding that a little bit, your xy, let's go back here. Here's your x, there's your y, okay? So your change all right. If you go back here, this is where they define that x and that y, and that's the definition for it, x and y there. So your f of xy is your f of x. There's your x value, and there's the y value, y0 plus t sine theta, minus f of x0, y0, okay, divided by t. Finally, by letting t approach 0, what are you meaning there? That P and Q are coming closer and closer together, basically Q moving toward P, so T is becoming 0. For each of the points P and Q, there's a corresponding point, of course. In other words, these are points on the xy plane. These are the corresponding points for P and for Q on this up above the xy plane in the realm of various z's. Okay. All right. So here's the definition. Word. If I had less than a half hour to go, which I don't, I think I could pull this off, but I've got to go get something else to drink. My head's clogging up again. Let's pause here again. I'm sorry to do this twice, but there's just something wrong. I don't know if it's the air in the room or what, but it's just not feeling it. All right, sorry about that. I'm back again. I don't know what's going on. My head's hurting. I feel almost dizzy, especially when I got up and moved around some. I just keep thinking it's because I didn't get enough to drink at lunch, but I'm not sure that's it. But I'm going to try to finish the class here. I've got another one later today. I hope I can make it through that. But anyway, let's go. So here's your definition of directional derivative. All right, got what we have here. F is a function of two variables, x and y, somewhere down there on the plane, both independent variables. And F is some surface above that plane. Could be below the plane, but let's just keep it above for now. X and y, function of two variables, x and y. U is this unit vector heading out in some direction here, theta, cosine theta I plus sine theta j. Just standard definition of a unit vector making some angle with the positive x-axis. Because it's a unit vector, its magnitude is 1, so its x component of 1 is the cosine of that angle theta, and the y component is the sine of the angle theta. Why? Because cosine squared theta plus sine squared theta is equal to 1. It's got to be, and these are the directions that it's going. So there's this unit vector. They've just sort of chosen at random a unit vector going out in this direction, angle theta. That's a unit vector. Then the directional derivative of F in the direction of that vector u, that unit vector u that you chose for some reason, okay, that angle theta was what you were interested in, is denoted by capital D, that means directional derivative, in the direction of u, so you subscript the u, that's a bold u, and it's a unit vector u, okay? The directional derivative in the direction of u of the function f. So that's what the d sub u f stands for. And here's what it is, function of x and y, f, function of x and y. The independent variables down on the bottom. Okay, is the limit as t approaches 0. Now t, remember, was the distance between your fixed point P and your variable point Q, I think it was, okay? And that t, you're going to let that approach 0. So the limit is that t is approaching 0, which basically you can think of your x approaching 0, your dx approaching 0 when you're doing a regular derivative y as a function of x. Now it's xy, so that t, which relates x and y together, okay, as that's approaching 0, of f of x plus t cosine theta, that was your q coordinate, y plus t sine theta, that's your y coordinate of q, minus f of xy, okay. You can kind of think of that as your, it's not exactly your point P, but I'm sorry, the f, it's the f I'm talking about. That's the value of your z up above this x and y value. X plus t cosine theta, that's the q place. Y plus t cosine sine theta, that's the y coordinate of your q vector. So this is f at q minus f at, think of that as your p, okay? So that's how far your function, the surface, is changed for a change in your domain, okay? Now, this is all assuming that limit does exist. Calculating directional derivatives by this definition is similar to finding the derivative of a function of one variable by the limit process. A simpler formula for finding directional derivatives involves the partial derivatives. Let's go with simpler, okay? This is too kind of esoteric here, okay? Nothing is very clear. How you chose your u, any of that, okay? So let's see. Here's the second definition here of your directional derivative, theorem 13.9. If f is a differentiable function of x and y, then the directional derivative f in the direction of some arbitrary unit vector u, which makes an angle of theta with the positive x-axis, so u is cosine theta I plus sine theta j, that directional derivative in direction of u of f of xy, just like we started before, but this time we're going to say the partial of f with respect to xy times the cosine of the theta plus the partial of y at xy times the sine of theta. So you see, rather than being a limit, and rather than that limit being a change of t and a change of y, and f at a change of y and a change of x minus f before the change, you just have the partial derivative of f with respect to x, cosine theta, partial of f with respect to y, sine theta. So, there are infinitely many directional derivatives of a surface at a given point. One for each direction specified by u, which would be any value theta you wanted to choose. Okay? Any value theta. And that would give you a directional derivative in that direction along that unit vector. Okay. All right. Two of those are partial derivatives, are the partial derivatives of f of x and f sub y. Direction of the positive x-axis, that's when theta is equal to 0, where u would be cosine 0, which is 1i, plus sine of 0, which is 0j. That would just be I. So the directional derivative in the I direction, f of xy, is f sub x, partial of f with respect to x, at xy times the cosine of 0 plus the partial of, with respect to y, at xy of sine 0, which of course, since sine of 0 is 0, why write the second one there? It's just your f of f sub x. I'm going to pause for just a minute. Dr. Bryant just came back. I need to see him for just a second. All right. Oops. Okay. And let me mark you as present, too. Thanks for being here. Second day in a row, you've been the only one here. Okay. What's that?
You still do the implicit partial differentiation?
Yeah, we're continuing with that. We finished the implicit differentiation, which was the end of 13.5. We got started in 13.6, which is directional derivatives. And that's what's coming up now. Now, I've talked for a couple of pages on this, so this is pulling up right toward the end of their discussion before they start actually working. Now, we're talking about directional derivatives. If you had xy plane, let's just count that before, okay, xy plane, both independent variables. You have some surface up here above this that's some function of x and y, okay, independently of each other, okay? If you pick any direction, let's say just from the x-axis, which will be that seam over there, just pick a direction there. There's a directional derivative of this surface here in that direction. Pick another direction here, there's a directional derivative with respect to that direction. So any direction you choose. Now they're saying, that's what they've been talking about up till now. Let's just pick two specific directional derivatives. One of these is f sub x, and one of them is f sub y. Okay? Now, at f sub x, the positive x-axis, okay, if you get your direction in that direction, in the direction of positive x, your angle there is 0, right? You're along that. So theta equals 0, your unit vector is then going to be cosine 0i plus sine 0j. Well, cosine is of 0 is 1, sine of 0 is 0, so this would just be 1i, which is I. That would be, your unit vector would be the I vector.
Why don't you say that so they're taking the derivatives?
Not yet. This is just picking values in the direction. the first direction we're going to pick is along the x-axis. So the unit vector in the x-axis is I. That's all that showed, which is just a weird way of going about doing that. Now, the directional derivative in that direction of I, of the function f of xy up here, whatever that function's doing, is your partial of f with respect to x times the cosine of 0, which is 1, plus the partial of f with respect to y, but that has sine of 0 is 0. So again, that's not in there. It's just f sub x times 1. Okay? That's the directional derivative in the I direction of the function f1. That's exactly f sub xy. Yeah, that's the direction with respect to x. I mean, the partial with respect to x. And same thing for y axis, which the theta will now be pi halves. So now you're going this way, no direction in x. Now the cosine of pi halves is 0, sine of pi halves is 1. So this is just going to be your j vector. Of course, the unit vector in that direction is the j vector. That's unit length. So the directional derivative of that function is going to be, this part is going to be 0, and this will just be f sub y. The partial of f with respect to the y direction in that direction. So they're just saying what we were calling partial derivatives basically are now directional derivatives in those two directions. There are infinitely other directional derivatives, and that I hope is what they're going to get to next. And let's go to that. Oh well, they go to an example now. Okay? Find the directional derivative of, here's your function. F of xy is 4 minus x squared minus 1/4 y squared. That's some surface. Okay? At the point 1, 2. Okay?
First thing we use to find the derivatives of it?
Yeah.
Do you take out the derivatives of it first?
Okay, we're going to find the partials of this function with x and y. And we're going to plug them in where they need to be down here. Okay? Now, at the point 1, 2. So x equal 1, y is equal to 2. All right. We won't worry about that point yet. But here's going to be our unit vector. That's going to be cosine pi thirds I plus sine of pi thirds j. Okay? And we know what cosine of pi thirds is. That's 1/2. And sine of pi thirds is square root of 3 over 2. Okay? For what difference that make? So we want the directional derivative in that direction. Okay? Now, as what I understood you to be saying, let's take your partials. Partial of x with respect to xy will be what?
It's going to be 0.
The first one's 0.
It's minus x.
Minus 2x. And the next part 0. Whereas your f sub y at xy is going to be?
It's going to be the first one is going to be 0.
Yep.
Then the second one is going to be 0.
Yep.
And it's going to be 1 negative. No, 2. It's going to be 2, right? No, 2/4.
2/4, which is 1/2
Yeah.
y. Right? Okay. There's your partial with respect to y. Okay. Now, all right, let's go back briefly to this definition here. This is before you came in. The partial derivative in the directional derivative in the direction of u of f of xy is the partial of f times the cosine theta plus the partial of f with respect to y times the sine of theta. We found our partials here. Now we're going to multiply them by these. Okay? So the directional derivative in the direction of this unit vector u, okay, of this function f of xy that we have here, here, is going to be the partial of f with respect to x times cosine.
It's going to be negative 2x, right? It's negative 2x.
Okay, and we're going to put that in just a minute. Yeah. Cosine pi thirds plus partial with respect to y sine of pi thirds. Okay, that's exactly what this thing told us. That is the directional derivative in those two directions. Okay, in that direction. Okay. Now, we're going to do two things here. We're going to plug these in, but also plug in the values. Okay? Okay. So this will, the directional derivative in the direction of that u right here, this is that u right here, of the function f, evaluated at any values x, y here, the partial with respect to x is minus 2 times 1. So that's going to be a minus 2. And what was the cosine of theta? Cosine of pi thirds?
Why did we use the x? Why did we use the x?
Because we want the directional derivative of this at that point. Yeah. Right. Okay. So that'll be 2 times, and what's the cosine of pi thirds? No, 1/2. Yeah, cosine of pi halves is 1. No, of 0 is 1. Okay. So that's going to be a minus 1 plus, and the partial of f with respect to y is minus 1/2. Well, minus 1/2 y, but y is equal to 2. So again, that's going to be a minus 1 times, and sine of pi thirds is, no, sine 3, square root of 3 over 2. Yeah, okay, okay, I thought you said it the other way. So what is that? Minus 1 minus root 3 over 2, which is, I don't know, you could write it as minus 2 minus root 3 over 2, or anything that you want to do that way. They left it as this one, minus 1 minus root 3 over 2, and they gave it as negative 1.866. So what that means is,
why did the second one use minus 2?
Well, I just wrote this as minus 2 over minus 2. Minus 2 over 2. And then put it over least common denominator. That's all I was doing. I thought maybe they'd write it in that form. They didn't.
Now, on the second form you have minus 2 minus square root of 3 over 2.
Okay. All right. To get common denominators here, this is a 1. Put a 2 here. That makes this a minus 2, right? Minus 2 over 2 is minus 1. Right? So put them over the common denominator of 2, you get minus 2 minus root 3 over 2. Yeah, it's just, I was just doing that in case you wanted. They didn't. They left it like this. Okay. So what this means, here we have the x-axis, here we have the y-axis. Our directional derivative is the unit vector at 60 degrees from the x-axis. So it's going to be something like this. And your shape is up here somewhere. But it must be going down because, yeah, it starts at 4 when x is 0, y is 0. It's up here at 4 on z, and it's going down because any direction you go, x or y, is going downhill from there. This is basically going to be sort of like an ellipse, you know, heading down the ellipse. So that's going to be the slope at this point. 1, 2, okay, the point right out here. Well, maybe we should just get started later, okay? All right, Justin's here. All right, we're in section 3.6, directional derivatives. And this is the first example in that section. And we're just describing what they mean by the directional derivative. Okay? So the picture of the floor as being the xy plane. There's x, there's y. Z would be going up then. And you're at an angle of pi thirds from the x-axis toward the y-axis. That's like 60 degrees here. You're going out 1 unit on x, 2 units on y, so you have a point here. The surface up here is defined by this, sort of an ellipsoid looking thing, and you're going downhill there, so your directional derivative is a negative, a fairly substantial negative value, not super big, but substantial negative value there. They say it's negative 1 point, I just had it, negative 1.866, so almost negative 1.9. Okay, that's the directional derivative in that direction. Another direction, it may be doing something else, but in that direction, that's the direction. At that point, there's your derivative. How much the function is changing as you change some unit vector in the xy plane. Okay? So that's how I did it. Let's see how they do it. Okay? Because f sub xy, they first start by taking the partial of f with respect to x, which is minus 2x. Take the partial with respect to y, which is minus y over 2. Both of those are continuous partials, so you can do this. If they were not continuous, you can't do this, okay? So f is differentiable. Since they are continuous, f is differentiable, and you can apply the theorem 13.9, which says the directional derivative in the direction of that unit vector u of this function, that function there, okay, is the partial of that function with respect to x times the cosine of this angle theta plus the partial with respect to y times the sine of that same angle theta. Okay? There's your directional derivative in that direction. Okay. Now, okay. So, plugging that in, your f sub x is minus 2x times cosine of pi thirds, well, they just put cosine theta, plus minus y over 2 times sine of theta. Evaluating this at theta equal pi thirds, x equal 1, and y is equal to 2, which is what they gave you back here. There's 1, 2, and there's your angle. Okay? Then that gives you negative 2 times 1/2, that's going to be a negative 1, plus a negative 1, when you put y equal 2 in there, times root 3 over 2, and that gives you negative 1 minus root 3 over 2, which is a fairly small number, negative 1.9866. Okay? Now, this is hard to visualize to me anyway. So here's your positive x-axis, positive y-axis. You're coming out 1 unit on x and 2 units on y. For the life of me, I can't see. I don't know why that 3's there. That doesn't make any sense. It's nothing to do with the problem that I can figure out. Okay, so you're coming out 1 here, 2 there. Here you are on the surface up here. Like I said, that's an ellipsoid looking surface there. Okay, the directional derivative is definitely going downhill at that point. Your unit vector is in this direction. Send that back to the origin here, and you see that's a 60-degree angle from the positive x-axis here to 30 degrees there. So here's your directional derivative, unit vector that gives you the directional derivative. Right? That's the u. Translate that over to this point, 1, 2, and that's the u here. Okay, and then go up here, and the directional derivative is that line there. Based on the change of f with respect to x, that's the partial of f with respect to x, partial of f with respect to y, and the amount of that that you're doing. So that is the direction of that light blue line here. That is your directional derivative. Slope of almost negative 2. Not particularly easy to see, I find. Okay. Now, there aren't doing example 2. So let's us go back and see if we can figure out example 2. Now, if you find it a little confusing, go to larsoncalculus.com for an interactive version of this type of an example. So here they say find the directional derivative of f of xy is equal to x squared sine 2y. Oh boy, what an interesting looking surface that would be at the point 1 pi halves, okay, in the direction of, IDO, in direction of this unit vector v, okay, which is, oops, no, that's not a unit vector. In the direction of the vector v, and that vector v is 3i minus 4j. Okay. So there's your vector v. Okay? Now, it might be helpful to draw, I'm going to come up here on the xy plane and draw that vector in here. 1, 2, 3, and I, 1, 2, 3, 4, and j. So here's that vector v. Now, obviously not a unit vector, but we really don't care. We're only interested in that angle there, theta, okay? And not really the angle, but the sine and the cosine of that angle, okay? Now, this is 3 units here, this is 4 units here, and this is obviously the square root of 9 plus 16. What is the slide here? What is the hypotenuse there? It's 3 squared.
No, the side, you have 3.
4, that's a 4.
Oh, okay.
Okay. Right, so what's the hypotenuse here? 3, 4. 9 plus 16 is 25, square root of that is 5, right?
Yes.
That's a 3, 4, 5 triangle. One of my favorites of all time, okay? Now, we're interested in the sine and the cosine of that. That's really all we're interested in. Well, what's the sine of that angle theta? Opposite over hypotenuse. Over 5. Cosine of that angle is 3 over 5. That's all we need from that angle. We don't care what the unit vector is. We don't care anything else. All we care about is what the sine and cosine is, ultimately. You could go back to unit vector if you wanted to, and it's easy enough to do. 3/5 I minus 4/5 j. Oh, I messed it up, didn't I? Sorry about that. There's a minus 4. Whoops. That's down here. Okay. So it's really down this way. Okay. Same thing, except it's a minus 4/5 and a positive 3/5. Sorry about that. Because it's 3i minus 4j. So, yeah. Those are the sines and cosines. Ooh, I already almost missed that. Okay. So what do we have to do now? Yes, find the partial of f with respect to x, and what's that? I'm sorry? 2x times the sine of 2y, right? Because you can't treat that as a constant. When you're taking the partial with respect to x, treat y as a constant, right? And since y is a constant, sine of 2y is a constant, or 2y is a constant, and then sine of 2y is a constant. It's just a constant. coefficient of 2x, okay? Just that. And what's f sub y?
There's going to be, because x over x would be a constant now.
Yeah, x is a constant now, right?
It's going to be sine 2 sine.
2x squared.
Sine.
Nope. Derivative of sine is cosine 2y. Exactly. That's your f sub y. But we're only interested in that at the point. Okay? So let's plug in what these are at that point right there. Okay? So f sub x at 1 pi halves is what?
We have 2 times 1, which is going to be 2. Sine of 2 times pi halves.
The 2 times pi halves is?
Going to be 2 pi halves.
Yeah, which is pi. And what's sine of pi?
Sine of pi is 0.
Yeah, all that for nothing. Okay. How about f sub y?
So what we have 2 times 1
Okay.
squares is just going to be 2 times cosine of 2 times again pi. Cosine of pi is 1.
No, it isn't. Cosine of 0 is 1.
Oh, cosine of 0 is
And cosine of 2 pi is 1.
cosine of pi. Oh, cosine of pi is 0.
Nope. Cosine of pi halves is 0. And 3 halves pi is what? Nope. Cosine of 2 pi is 1. Cosine of 0 is 1. What's cosine of pi? Say again? Wait. Not a half. Cosine of... Cosine starts at 1.
Yeah.
Pi halves it goes down to 0. And pi goes down to... -1.
I forgot the negative sign. That's
All right.
I know he's. I'm like, I know he's 1, but I forgot the sign. That's the. I'm like, I know he's 1, and you said no. I'm like, oh man, did I? I was like, okay.
So -1 times 2 is
Yeah,
-2.
He got me. He got me. I'm like, he got me 1.
I didn't ask for the absolute value of the cosine there. I wanted the value of the cosine there. Okay.
I automatically did it after that. So.
All right. So there we've got all that we need. So now the directional derivative in the direction of v, I'm not even going to call it the unit vector, okay, direction of v, of this function f at xy, and this xy happens to be 1 pi halves. This is going to be, your f sub x is 0, so don't even bother writing that one down. Okay, times the plus the f of f sub y, which is -2, times the, okay, f sub x is times the cosine, f sub 2 is times the sine, and what was the sine of your theta? -4/5. So this will be 8/5. 1.6. Okay? Yep. That's what they got it to be. All right. Now, this indeed is the same as if you'd made it u, the unit vector 2. Either one, it's in the same direction. And you just want to, the main thing is to get the sine and cosine right. Okay? And those are going to be, make a unit vector. So when we chose those, we made it a unit vector. Okay. And that's exactly what they got as well. All right. Now, do we have time to get started on the gradient? Huh? 5 minutes? Okay, so let's go. Oh, wait. Did we do this? I think we did. Let me erase my... Yeah, we did this.
Hey, this was number 1.
Yeah, that was the first one. Okay. So here's the gradient of a function of two variables. Okay? The gradient of a function of two variables is a vector-valued function. Notice the directional derivative is a scalar quantity. Okay? But the gradient of a function of two variables is a vector-valued function of two variables. And here's the definition for it. If z is this function f of xy, somewhere up here, okay? It's a function of x and y such that f sub x, the partial of f in the x direction, and the partial of f in the y direction both exist, then the gradient of f, and the symbol for that is this bold upside down triangle, okay? It's often called the del or a grad. Del f, and another notation is called grad f. And your calculators, you see, will sometimes calculate that gradient for you, okay? But that symbol is called the del. It's bolded, so when I write it, I put an arrow over it as if it's a vector, okay? And that indicates this thing is a vector quantity, okay? The grad f, or the del f of xy, is the vector. Here's what it is. Del f, gradient of f at xy, is the partial of f at xy times in the direction of the unit vector I plus the partial of f with respect to y times the unit vector j. So this doesn't quite do the same thing as we did before, but similar.
Hey, Doc, so the study class, one guy get to keep.
Oh, yeah. Oh, absolutely. Sorry. I thought about it. I had it on, but I didn't.
Get it back to you.
Okay. Okay. So the only difference here, what we had before when we were doing directional derivative, was this gradient, this partial times cosine theta, this partial sine theta. Now we're not using those, we're using the unit vector, so this makes this a vector. So this symbol, del f, okay, gradient of f, is also, it's a vector quantity. And another notation for it is grad f, okay, meaning gradient of f. And in this figure, note that for each xy, the gradient is a vector in the plane, not a vector in space, a vector in the plane, okay? The plane down here, because it's just ij. It's not, there's no z component in it. It's a vector down here, okay? Now, so it's a little bizarre in that you're talking about a function up here, that's the function, but the gradient is down here in the plane, in the xy plane. That's the direction that you're going, okay? Now, what's even more interesting is what that means. And I'm not sure we're going to have time to do what it means today, but the next thing we'll do is actually calculate those gradients. So we will begin next time on example 3. Now, let's see. Yeah. So that's where we'll begin. There is a little note here. Notice that there is no value. Let me go back here. Notice that there is no value is assigned to the symbol del itself. Okay? It is an operator, just like d by dx was an operator telling you take the derivative with respect to x of whatever follows it. Okay? This is saying take the gradient of this function that follows it. Now, here's the deal here. This is a scalar function. You operate it on that, it becomes a vector. Okay? So here, this is an operator that takes you from function space to vector space. Okay? For whatever that's worth. And we'll begin next time with example 3, because I believe we are out of time now, aren't we?
Yes,
yeah.
right on time.
Right on. Oh, amazing. Okay. All right. Well, sorry, I got started a little late today, so we didn't get as much covered, but I'm glad y'all finally were able to come for a little bit of it.